Thank you all for joining the session. My name is Satish Bandhu. I'm the technical leader for CFD at PLM, and I'm your host for this session. Welcome you all to the fifth webinar in series on the topic of modeling complex motions for effective realism through simulations. The outline of the session is as shown here. Firstly, I would like to take this opportunity to introduce our company, PLM, on who we are and what we do. I'm not going to spend much time here, and then we move on to the brief introduction to STAR-CCM An as a safety code, as well as the integral part of complete PLM solution offerings from Siemens Digital Enterprise. Finally, we spend much time on topic of the day, modeling complex motion, and for that matter, we will see the motion analysis within STAR-CCM by briefly discussing about various models available within the code, along with some interesting applications from various industries, and followed by a Q&A. PLM as a company have multiple industry experience ranging from oil and gas, machinery and equipment, petrochemical, nuclear aerospace, and we are based out of Houston in Texas. And PLM is a smart expert solution partner to Siemens PLM products as STAR-CCM An, Nextnaston, MSC, Battery Design Studio, HEATS for multidisciplinary design optimization, and flow-induced, which became a part of Siemens Portfolio after the Mentor Graphics acquisition. And we are mainly a team consisting of PhDs and masters from different backgrounds of solid mechanics, fluid mechanics, materials and corrosion, numerical analysis, and optimization. As a company, we provide engineering consulting services, and we also cater our services to the automation and customization needs of the organization. And when it comes to the CFD, PLM have capabilities with its rich consulting experience by delivering some interesting and challenging projects successfully for oil and gas and process industries. And some of the projects include physics like erosion, corrosion, fluid structure interaction, mixing and separation, and some of them also included acoustic source modeling. On the marine and offshore industry side, PLM has experience with jumper VAB, vortex induced vibrations, floating systems, ship dynamics, risers, and pipeline VA. A brief introduction to Simcenter STAR-CCM. Simcenter STAR-CCM is a multi-physics solution for CFD engineers. With its single integrated user interface, STAR-CCM helps user to cover complete application scope with a broad range of validated models for various disciplines. And the physics is not just limited to CFD, but also extends to other high-end topics like electromagnetics, multiphase flows, particle dynamics, reacting flows, electrochemistry, aeroacoustic analysis, computational rheology, and solid mechanics. Here we can see some interesting animations covering a wide range of industries where STAR-CCM has been used. We see an application from automotive industry, material handling. We see an excavator picking up some material using its bucket, and we have a gas turbine example, internal combustion example here from the automotive industry, and then we have marine example where two vessels are connected to each other and then while they're floating on the free surface. And in addition to these extensive physical models available in STAR-CCM STAR-CCM as a code have a comprehensive set of various models to take into account of the body motions and mesh motions, namely mesh morphing, Overset Mesh, and 6 degrees of freedom by approach called DFBI, dynamic fluid body interaction. And this is the topic of this session, where we extensively cover up all these mesh motion and body motion techniques implemented in STAR-CCM Plus. And I also want to mention here that Simcenter STAR-CCM Plus is a part of a bigger portfolio called Simcenter, and that combines the best-in-class CA simulation. STAR-CCM Plus falls under this category, and then there's a system simulation and testing solutions, as well as the design, exploration, and analytics. So all these solutions work together under one umbrella called Simcenter, helping engineers to innovate and bring products faster to the market with greater confidence. The overview of modeling motion in STAR-CCM Plus. Before we get into the techniques and methodologies implemented in STAR-CCM Plus, it's good to have a look on different applications. Here we see some interesting animations. So all these animations are from different industries where one or the other methodology, or even the combination of the methodology we're going to discuss, which are Overset and DFBI used in these applications. To start with the first example on the top left corner, where we see two racing cars, and one of the racing car is intended to overtake the other. And this motion, the overtaking motion, is modeled by Overset. And another example from the automotive industry, where the panels are being painted by moving the paint nozzle, and this moving paint nozzle is modeled as the motion of this nozzle is modeled as Overset object. Similarly, we have other examples from the marine, material handling industry, and aerospace. We see some nice structures, the flow structures, when the propeller is rotating, when we see the top view. And here also we see vertical takeoff, the aircraft, where we see the motion is modeled using one of the techniques, either Overset or the DFBI. So when it comes to modeling the motion today, so it's beyond the need of simply modeling complex motion. Today's the industry's demands from the simulations are at great depth, and they can be well listed as key requirements as shown here. The need for effective realism from simulations requires sophisticated interactions of various physics involved in any given example. For example, we see rainwater management application from the automotive industry, where we see the wiper blades are moving relative to the windshield. And so to solve these kind of problems, one has to have methods to support the objects which are moving and against other objects and overlapping on other objects, or sometimes they are completely immersed in other domains. And also, apart from that, there's a need to solve different physics across all these regions, be it the region which is immersed in other region, or overlapping region, or sliding region. So here, in this example, the physics need to be solved, or the physics for the rainwater as the rainwater droplets, and then once the rainwater impinges on the windshield and it creates a fluid film, then there is a need of physics to solve the fluid film and also the air around the vehicle in its operation. So all this physics need to be solved across different meshes. So this is this is the need of the sophisticated interaction of both moving objects, as well as the physics need to be solved across the different regions or domains. And it's not just a simple motion anymore from the industry point of view. And there are a good number of examples where there's a need to predict dynamic motion of bodies under interactions of various physics, which demand, again, a true 6D view of capabilities of a CFD code. Here in this example, what we see is a wave energy convector floating on the free surface of the waves. for the purpose of power generation. And predicting its as installed behavior requires means to include the mechanical connections like ropes, hinges, and springs into the modeling approach. And other key requirement from the industry when it comes to modeling the complex motion from the simulation point of view is to support the multiphysics. Here again, in this example, we see an exhaust system application where we see a static guide vane in installed configuration, which is undergoing some structural deformations. And the modeling approach must have the ability to accommodate these changes on the fluid side. When the structural member, the component deforms, that should reflect on the mesh deformation on the fluid side. So this is a key requirement from in this kind of similar examples. Another key requirement is the prediction of the mechanical performance of rotating machinery, and which is highly depends on the how accurately the motion is modeled. Examples of fans, systems like fans and pumps, propulsion systems, where their mechanical performance is highly dependent on how accurately you model the motion, be it a rotating motion or any other motion, complex motion. And also the aeroacoustic performance of the tilt rotor aircraft, which we see here in this animation, highly depends on how accurately the motion, rotating motion of these propellers are being modeled. And the final requirement from the industry is to have an ability to define a prescribed motion. Few people call it a defined motion. So here in this example, what we see is a water flooding simulation, and it became a standard analysis item these days, almost performed by all the automotive companies in the world. And in this example, it involves a certain path for the vehicle to enter into the pool of water for the flooding studies. And on the top of it, it also requires model to take the fluid forces acting on the vehicle into account. And similarly, in the other example for excavator, the bucket which is collecting the material need to be modeled with some designed or defined motion. So the mesh motion modeling techniques and methodologies should address all these key requirements. And for that matter, Simcenter have answers to all the needs of industry to predict real-world behavior using its mesh motion techniques to drive innovation. And the offerings from the Simcenter STAR-CCM Plus are easy to use Overset technology and advanced DFBI dynamic fluid body interaction with body connections and forces. And for applications like fluid structure interaction, there is a need for mapping and interfacing between the physics need to be solved on the structural side and the flow side. All these mapping and interfacing requirements are well covered in Simcenter STAR-CCM Plus for the FSI kind of problems. And there is also need to have a different modeling technique, motion models. So again, Simcenter STAR-CCM Plus have a handful of powerful motion models which can seamlessly work together towards achieving the effective realism for the motion. So in this session, we are mainly focusing on both Overset and DFBI as part of all the key requirements which just covered up here in the previous slide. The Overset Mesh implemented in STAR-CCM Plus is very easy to use and it's very robust to use. It is supported by all the grid types in STAR-CCM Plus. As you might know, that STAR-CCM Plus have different types of grid types, namely polyhedral, trimmer, tetrahedral, and can efficiently simulate a very complex systems involving complex motions such as the difficult motions in positive displacement machines, gear lubrication. Here we see two bevel gears mating each other. So these kind of complex motions can be easily handled, modeled in using Simcenter STAR-CCM Plus. After the overset mesh methodology, the second topic we're going to extensively cover is the dynamic fluid body interaction, just to give an overview before we get into detailed picture of the DFBI. So DFBI method helps to define bodies that move under influence of the fluid forces. And also it offers flexibility to constrain some of the degrees of freedom in any given direction. Besides the fluid forces, when we use the DFBI method in STAR-CCM, it allows to include other external forces like the propulsive devices, bearing, drag, and gravity. So here in this example, we see a mechanized boat which moves with the help of a propeller. And this mechanized board is modeled as a DFBI body. And the propulsion force which it's experiencing is modeled as an external force on top of the DFBI body, experiencing the fluid forces coming from the free surface. In addition to that, if there are two DFBI bodies need to be modeled, and if they are connected to each other by some hinges, joints, or moorings, like we can see in the top example where two vessels being connected with each other by some moorings and joints while they're floating freely and under the influence of the free surfaces of this water body. Before we get into the much details of the Overset and the DFBI, let's have a look at the tools to define motion available in STAR-CCM. And I think it's good to discuss about these tools available in STAR-CCM by going through a STAR-CCM session. Here we have a STAR-CCM session opened. And here, if you see under tools, in the main tree, you can access to define motions. And here you can see a list of motions available, starting from rotation, translation, morphing, DFBI-based motions, and there are harmonic balance flutters, solid displacement purpose applications, and finally an option to define a trajectory. To demonstrate a simple rotation setup, case is already prepared and that is open here. Here you can see under the tools, under the motions, you can see two motions for rotation have been defined. Here in this example, we see a satellite which is rotating and revolving around Earth's miniature model. And the revolution and rotation of the satellite around rotating Earth model here with given rotation rates. Here you can see a satellite which is placed around Earth miniature model. Here the idea is to see how the satellite is rotating and rotating around its own axis and revolving around the Earth. So once we have these motions defined, they must be assigned to the respective objects. So the motion defined for the satellite revolution and rotation has been assigned to the satellite body, and the rotation for the Earth is modeled to source, which is Earth in this case. Here we can see once everything is set, once we run the calculation, you can see the Earth is rotating and the satellite is revolving around Earth and also rotating with its own axis. That's how you can able to set up other motions available in the STAR-CCM for various complex motions. And the second model I would like to touch upon is the trajectory, which you might find it interesting. Here again, this is a already set up case opened in STAR-CCM session, and here you can see in the motion. Here you can see the motion, the trajectory is already defined. And when you use trajectory, you need to define the path using which your body or object moves. That need to be defined as in a tabular format. Here we can see the trajectory, and under the trajectory, you can see a table consisting of X, Y, Z, and the speed specification. So all the path has been imported into STAR-CCM Plus as a CSV data format, and here once you have the table available, you can uh, uh, use it in the trajectory definition. And also to define the motion, you need to have a velocity here. The velocity is defined. Uh, once you have that, you must define the trajectory motion to the object which you want to move. Um, so let me move it further. You can see. So this. And it's not moving further. Let me see. Okay, let's wait for a moment. It will progress on its own. Yeah, here you can see the table has been defined. Table is imported, and then that has been assigned to the trajectory. And also you can see the velocity. There's a scalar field function is written for defining the velocity with which the body, this dummy toy car is destined to move on this defined path. Yeah, so this is the region which need to be assigned with the defined motion using trajectory. And once we all said, we can, and also to make it more realistic, we can define the distance between the two wheels, the front wheel and rear wheel as offset, and which can give you more realistic motion. So here you can see once we start the calculation, it's the toy car is slowly moving along the path which is defined using the trajectory. So here you can see using the managed rotation option in the form of offset distance, you can see the motion or the movement of this toy car in a more realistic way. That's it. Next topic is the detailed discussion on the Overset Mesh methodology, and it's some good examples of Overset Mesh. So it's worth to mention here that the STAR-CCM Plus is the first commercial CFD software to implement this well-proven moving mesh technology, which was prior used by NASA research. And the NASA guys call it as Chimera mesh. That's the other name of the Overset mesh. And in the traditional CFD codes, it's not possible to model the relative motion between the bodies without having this kind of moving mesh technology. In STAR-CCM Plus, this Overset mesh is implemented almost a decade ago, and it got significantly improved all these years with many useful features and capabilities added to this methodology, and which makes this implementation very unique when compared to the implementation of the same Overset or Chimera mesh technology in other commercial softwares. And in the Overset mesh, the key technique is to have the object need to be moved, has to be defined as a separate region. And once you have a separate region for the object to need to be moved, you must mesh it separately. So here in this example is flapping airfoil. This flapping airfoil is defined as a separate region, and it's superimposed on a background region having a different type of grid, different grid type. Here in the flapping wing, which is modeled as a Overset region, having a polyhedral mesh, and this is overlapped on a background region having a trimmer kind of mesh. And this is the key technique of central to the Overset mesh. And as I said, the Overset mesh methodology, it's all about information exchange business between the background region and the Overset region. And the workflow we see here, it depends on it's according to the information exchange between the background region and the Overset region. To better understand the workflow, here we have an example of again, we have seen the one of the animation of this same in the initial early slides of the presentation. So here we have an example of two racing cars, and one of them, the rear racing car, is intended to overtake the front one. So to solve this problem using Overset technique, what we need to have is as a first step is to have two different regions. One for the background region containing the racing car at the front need to be overtaken, and the second region for the racing car which is intended to overtake the first one. And once we have two different regions, and then they must mesh separately. Here we can see we have two meshes, and the rear racing car have a mesh which is colored in red, and then you can see there is a zone which is colored in blue color here. So in this zone you can see the cells are overlapping in from each region. And once you have these meshes ready, and the next thing is to create the outer boundary of this Overset region as a Overset mesh type. And once you have this interface defined, that led the information to be passed from the background between the two regions or two meshes. And once we start the calculation, we can see that the overlapping region will update according to the way the object need to be moved, or by the definition of the motion. So here we can simply define a translation motion to this rear racing car, and then as it moves towards the front racing car and overtakes, its overlapping region will be automatically updated, and the information is passed between the two regions simultaneously on the fly as the solution moves on. And to further understand the techniques behind the methodology behind the Overset mesh method, it's good to understand the terminology used in the Overset. So here we have different colors starting from the cyan and yellow color, so the active cells which are colored by cyan and yellow, where the discretizing counting equations are solved. And we have a passive cells colored in dark blue, where, as the name implies, no equations are solved. And we have other type of cells which are colored in green, we call donor cells, and they are used for information exchange by interpolating the information, the calculation of the field variables between different cells. Again, so another way of looking at the Overset mesh methodology. So here we have active cells from the background region, which are colored in green color, light green color, and then we have passive cells colored in red color belong to the background region. And once we have this overlapping region on the background region, we have active cells again colored in light green color from the overlapping region. And in both the regions, we have acceptor cells colored in dark blue. And as a result of that, we see the information passes from the one region to other region. So here we have cells from the background region and cells from the Overset region. And once we assemble them, we have the final mesh looks like this on the right side. So here again, this can give further understanding. So here the information is starts from the active cells of the background mesh, and the information passes to the acceptor cells of the background region. and from the acceptor cells of the background region, the information goes to the acceptor cells of the overset region. And then from there, it's go to the active cells of the overset region. Again, the information goes back in the same path in a reverse direction, because like in this case, it's a simple, the object need to be moved is a simple boat, and we have a wall boundary condition. So using this boundary conditions, the solution will be updated in the active cells around the body need to be moved in the active cells, and then that information will go back to the acceptor cells of the overset region, and then from there it goes to the acceptor cells of the background region. Then from there it goes to the active cells of the background region. This is how the information flows in two directions as the solution progresses using the overset technique. And there are two different options to define the overset mesh interface. And the way, so one is the overset mesh interface, another one is overset mesh zero gap interface. As the name implies, zero gap, they both differs the way they handle the zero gap. In some of the examples, while modeling the relative motion between objects, sometimes there is a need to handle the small gaps. And if it is a small gap, need to be resolved. So the preferred choice for the interface is the overset mesh interface. And if on the other hand, if the gap is zero gap, and it's then there is a need to close the gap in a tight manner, so the preferred choice is the overset mesh zero gap interface. Here in this example, we see a sphere. A sphere is touching the ground, and then we see there is a small gap, and that need to be resolved and preserved. So using the overset mesh, keeping a overset mesh interface, by keeping at least 4 cells in that closed gap, we would able to resolve that gap between the sphere and the ground. The example for the overset zero gap interface is, you can see here, it's again the spherical valve here in an internal application where it's when there is a high flow, the spherical valve is lifted up, and then when there's no flow, it touches the inner walls of this component, and then it's a scenario of zero gap between the sphere and the walls. And to solve these kind of problems where there is need to have a zero gap interface, the approach is to have the overset zero gap interface between the overset region and the background region. So here in this case, the background region is the domain inside this internal equipment, and then there's the sphere is modeled as a overset region embedded inside this background region. So the typical uses are when there is a need to seal the flow completely as a result of the zero gap. This interface option is preferred, and on the other hand, if there is a need to resolve the collisions and contact, again you can use this kind of zero gap interface. And typical applications include positive displacement pumps, valves, and the control surfaces from the aerospace industry, where when they operate, in some scenarios, the gap between the control surfaces is completely tight, and it's zero gap. Another feature in the overset mesh technology is the ability to model the overset interface as dynamically as an interface and also as a wall. Here in this example, this is a medical example here. What we see here is the tooth is implanted, and it's and the motion of the tooth while it is in the implanting is modeled as using the overset mesh. Here we can see two overset regions. You can see two circles moving against each other. So the top one is moving against the bottom one, As it moves close to the bottom one, the Overset interface becomes the wall boundary. And here you can see while it is approaching towards the wall in the bottom side, it becomes the wall. So using this option in some of the examples or application where there is a need to dynamically change the interface to the wall, this option is quite useful. Another feature or an option available in the Overset Mesh technology is to have both Overset Mesh and boundary interfaces in the same simulation. Here in this example, we have two cylinders, and there is a star-shaped region, which is, while it is in motion, it's overlapping with these two cylindrical regions. And when it is in overlapping scenario, it automatically assumes that it's a overlapping interface, and when there is no overlapping, it becomes the boundary interface, with like a wall or some other interface. So so this option is useful in applications like gerotor pumps or gear pumps or scorer compressors, where this kind of feature is much needed. And there is another option for the topology to be defined in Overset Mesh that's called piston motion. Again, as the name implies, piston. This is useful for the applications in cylinder modeling applications. The difference between other features is that when the Overset region moves to other position, it automatically removes the background region on the fly. Here in this case, as the piston moves from the BDC, the bottom red center, to the top red center, so it automatically deleting the background mesh. So this is again a much useful feature for incident applications and linear dampers. Again, linear damper is much similar to the incident where you have a damper moving inside a cylindrical domain, and also from the oil and gas applications in pipelines to clear out the dirt. The pigging, they move the pig inside the gas pipelines, and the pigging analysis can be modeled by using the piston motion feature implemented in Overset Mesh. And the final feature in the Overset Mesh is the Prism layer shrinkage. Here, in this kind of screw compressors, when they are in operation, when they come in contact with each other, so there is this very small gap, and then there's a need to have a numerical stability by controlling the mesh, prism layer mesh between those tiny small gaps. So using prism layer shrinkage, you can have a more robust calculation by compressing, by shrinking the prism layer in the areas of interest. The typical applications include, again, the throttles, valves, and pumps of type positive displacement screw and gear pumps. With that, the second topic of the day is the DFBI method, dynamic fluid body interaction method, and its applications. So DFBI method is useful. Again, it's repeating. We already discussed about this one. So it is used for the scenarios where the body, under the influence of the fluid forces, displaces or moves. And when we use the DFBI method, it in the background, it solves the Newton's second law of motion in a point mechanics approach. And on the top of solving the fluid forces acting on the DFBI body, you can also combine other forces, external forces we have discussed in the previous slide, the external forces of propulsion forces and the connectors in the form of hinges and springs. Typical applications
marine ships, rotating machinery, and ballastic motion, store separation valves, and pistons. Within the DFBA, there's an option called Meshless DFBA bodies. Here in this example, we see an excavator is excavating some material from the pit. So here, if you use this Meshless DFBA body, namely mechanical body, only the bucket is part of the modeling, and the other connecting mechanical components are modeled by external forces in the form of hinges and joints. So that way we can save a lot of computational time, unnecessarily having mesh and keeping them as part of the computational domain. And typical applications include linkages connected to pumps. Again, these linkages can be defined as mechanical bodies, as the meshless DFB bodies only. The pump, the internal flow inside the pump can be modeled using a DFB approach. And armature actuation, again, this is a medical device application where this meshless DFB body application feature can be used. Another option available in the DFBI to model the complex geometry is to have the forces, to include the forces and couplings acting on the DFBI bodies. Here, in this marine example, the component which is dropped into this free surface water, free surface, has been connected to some catenaries, and all these mechanical connections can be modeled easily, efficiently using these options available in the DFBA framework. So the couplings can be modeled as linear springs, catenaries, contacts, and then joints can be modeled as spherical or revolute joints. And sometimes, if there is a need, the user can have their own defined couplings and connections using this option. So there are applications where both Overset and DFBA can be used. In this example, we see one example from the aerospace and another example from the marine industry. The store, which is separated, model as a DFBA, and the motion is model using the Overset. So both the models are used to get the realistic behavior of the bodies under this phenomenon, like in the store separation, and then the boat, which is the slamming on this free surface. So all these physical behaviors can be efficiently modeled by using the combination of DFB and Overset Mesh. Besides modeling the external forces, there's also it's also possible to model the contact forces acting in the DFBA along with the Overset Mesh. So when here in this example we see a spear which is falling on the ground, and the contact forces which it undergoes by interacting with the ground, they can be modeled using contact forces on the DFBI body or object. And frictional forces also can be modeled as additional forces on the DFBI body. So the external connections, it's repeating here. You can see these two ports modeled as DFBA body. They are connected with mechanical connections in the form of hinges, and then when they're connected with external connections, and all the forces and moments they undergo can be simultaneously calculated using the DFBA approach. This is the final topic of the session. So the latest features for the motion modeling implemented in recent times in the STAR-CCM Plus, starting of this year 2020, in the latest release of STAR-CCM Plus, is the adaptive mesh refinement, and it's implemented as a model-driven method. And there are two implementations. One is the free surface model-driven adaptive mesh refinement, and another one is the Overset-driven adaptive mesh refinement. And this feature is as a new feature related to the Overset
mesh motion technique or complex mesh motion needs of the simulations. Here in this example, we see the way the adaptive mesh refinement is working. Here again, this is a marine application. Here, the free surface has been resolved by adaptively refining the mesh by AMR technique here, and also it resolves the water splashing uh, uh, by this AMR approach, and it's easy to use with minimal uh, modeling parameters, and it's useful to reduce the engineering time because you can minimize the manual intervention, and also you can avoid uh, more number of cells. So only uh, using the adaptive mesh refinement technique, it only keeps the cells, final cells, and much more cells where it is required. So that ways you can save a lot of computational efforts and time. So the Overset Mesh model-driven mesh adaptation. Here you can see this example. This is the oil cooling of oil lubrication of the gear. Here, using the adaptive mesh refinement, this free surface have been resolved. Free surface of the oil splashing has been resolved. Here, using this technique, you can avoid unnecessary refining of the entire path because the Overset is used for in some of the application to when there is a motion at a large distance. So instead of resolving the whole path using the AMR technique, you can only automatically adapt the mesh without having upfront unnecessary refinement for the mesh. So the same thing you can see here in this booster separation example. So here, when the boosters have been separated, you can see there's a refinement around the whole rocket with the boosters. So here, the mesh is automatically updating and using the AMR to capture the separation effects of the boosters. Previously, without AMR application, one has to have much refinement to the entire course of motion of the booster separators when they separate from the rocket. So by that way, we can reduce the computational efforts and time using the AMR technique. Typical application includes, as we see here, the gear lubrication and stage separation, where the booster separates from the rocket and at high speed. Here again, to have an idea, again, I'm playing the animation. So when the booster separates, you can see the mesh is propagating with respect to the separating boosters. So you can see the mesh interface, the mesh coarsening interface is moving, expanding as the booster separator separate from the rocket. Yeah, with that I conclude, and happy to have a questions if you have any. Please feel free to have any questions if you have. Any questions from the attendees? Thank you for joining this session.